Okay, good morning, everybody. Okay, so in the previous class, we start talking about the FIR filter, and we looked at the main advantage of the FIR filter, and we said that if we have an FIR filter, then if we have some symmetry, we can ensure the filter will have linear phase. And what was the advantage of having a linear phase?
No distortion for different frequencies.
There is no distortion for different frequencies going through the system. All of them are going to be delayed by the same amount of delay. And then we said, we looked at the requirements for having a linear phase. And we said in order to have a linear phase, we must have symmetry. We must have either odd or even symmetry about the center of the impulse response of the filter. Make sense? So if you look at the 4 different cases, or did we look at 4 different cases or not? We did not?
We looked at 4 different symmetries.
Oh, here. Yeah. We should have either even symmetry when the number of the impulse response length is odd, even symmetry when it is even, odd symmetry when it is odd symmetry when it is even. And we did not derive, we wrote the expression for the frequency response of these filters, and we said we're going to take one of them and derive the frequency response for. So we took the case when n is odd and we have an even symmetry, and we said we're going to derive the frequency response and show indeed that the phase of the filter is going to be linear. So we took the impulse response of a filter that is of odd length, and it has an even symmetry that we see on the board. You know what the symmetry means, everybody? So it's symmetrical around the center of this point here. So if you look at this filter, we're going to write h of e to j omega, which is h of z equal e to j omega. So it's going to equal the summation from n to n minus 1, h of n e to negative j omega n. And then we said we're going to divide this summation into 3 parts. This part, people online do not see. We're going to divide it into 3 parts, the one highlighted in yellow, the one in purple, and the one in blue. And therefore, is going to equal to the summation. The purple is the one at the center, h of n minus 1 over 2. And then we have the summation of the yellow from 0 to n minus 3 over 2. Then we have the blue from n plus 1 to n minus 1, h of n e to negative j omega n. And then we took the summation that is in blue, and we said we're going to replace m with, we're going to replace n minus 1 minus n with m. So if I come here, we're going to replace n minus 1 minus n with m. And therefore, the summation is going to be from when n is equal n plus 1 over 2, we're going to have m that is equal n minus 3. When n is equal to n minus 1, m is going to equal to a 0. So therefore, the limit of this summation is going to also equal to the limit of the yellow summation. Does that make sense? Yeah. Okay. So then we replaced, we can take the summation from 0 to n minus 3 over 2, and we can replace h of n minus 1 minus n with h of n, because there is a symmetry. H of n minus 1 minus n is equal to h of n. And therefore, we have the summation from 0 to n minus 3 over 2 h of n e to negative j omega of n minus 1 minus n over 2. And what we've done here is we've taken e to negative j omega multiplied by n minus 1 over 2 as a common factor out. So it's going to shift all the phases inside the summation. Okay. So then, when we look at this summation here, we can write this as 2 multiplied by h of n, and we can replace the phases with a cosine of omega multiplied by n minus 1 over 2 minus n. And therefore, this is going to represent the magnitude of the frequency response, and this is going to represent the phase of the frequency response. And as we can see, the phase is linear. It just, the phase as a function of omega is just a constant multiplied by omega. And therefore, we have a linear phase. Okay. Any questions? So we can do something similar and show that for all the other types, we can write the frequency response as a linear phase multiplied by a magnitude when there is a symmetry. So whenever there is a odd or even symmetry, we have a linear phase, which we said is something that we like to have on our filter because it means the filter is not going to suffer from distortion. Okay. So with that, we can look at designing our filter. FIR filter design. So we're going to look at how we design different types of filter. We're going to look at the low pass filter, a band pass filter, a high pass filter, and a band stop filter. So we're going to look at an ideal filter, and then we're going to see how we can get a practical filter from this ideal filter. So let's look at the ideal filter. Okay. So if I have a low pass filter, and actually let me just have one common axis for all these. Does not look very neat, but I'll use another color. Hopefully that will make it clear. If I have a low pass filter, then I have a frequency response that looks something like this. This is h of omega or h of e to j omega. Low pass filter. We can have, and we're going to call this omega 0, and this is our filter. And if this is the frequency response of our filter, what is the impulse response of this filter? Anybody want to guess? A sinc. So this is going to be a sine omega 0 multiplied by n divided by pi multiplied by n. So if I have an impulse response that looks like this, then the frequency response of this filter is going to look like ideal low-pass filter. The second filter is a band-pass filter, which is going to look something like this. We're going to call this omega 1. This is omega 2. What is the impulse response of this filter?
Is it sync with
Good guess. What else? How about if we have it as a sink like this, minus a sink like this? Okay, so we're going to have h of n equal to sine omega 2 multiplied by n divided by pi multiplied by n minus sine omega 1 multiplied by n multiplied by pi multiplied by n. Again, the bigger sink minus this is this minus this. Okay, if we have a high pass filter, who wants to guess? Oh, let me plot it first. What do you think the impulse response of this filter is going to be? How about a delta of n minus sine omega 0 n divided by pi multiplied by n? What is the frequency response of a delta? A constant. If I take a constant and subtract from it this, what is it going to be left? This. Okay. How about a band stop filter? This is omega 1, this is omega 2, and this goes all the way to a pi. H of n going to equal delta of n minus sine omega 2 n divided by pi multiplied by n plus sine omega 1 n divided by pi multiplied by n. Make sense? So the band stop filter is just a delta minus a band pass filter. I took a constant, subtracted from the band pass filter, I'm going to get the band stop filter. Together? So this is great. So if I want to build any of these filters, this is the impulse response of any of these filters. What is the problem with this impulse response? It's infinite. Excellent. It is infinite. So ideally, we can have it. Practically, we have to have a finite impulse response. So to practically design a filter, again, this impulse response is infinite. How do we make it not infinite? We chop it. What do we call that process of chopping the impulse response? Sampling? No. I mean, it's already discrete. Windowing. What is windowing? If I look outside, if I look at the horizon, you can see like 360 degrees. But if I have only one window, I'm going to see only part of that view. So we do the same thing. So we're going to use window method is used. Okay. So therefore, we're going to start with non-realizable filter. And then we will alter h of n to get a causal and stable finite length h of n. let's call this h of n ideal to get a finite length h of n. Okay. So therefore, what we're going to have to do to get a causal and finite length impulse response, we're going to truncate, and then we're going to weigh the desired impulse response. And then we're going to shift to make it causal. Together? Make sense? Okay. So what we're saying is that from the previous page, if I look at the impulse response of any of these filters, it's going to look something like this. This is 0, this is n, this is h of n. Again, this is, it's ideal, and it's not practical because it goes from negative infinity to infinity, and it is also not causal. So therefore, what we're going to come and do is we're going to apply a window. So we can consider this our window. So we're only going to keep the components of the impulse response that are within the window. And then we're going to shift the impulse response to make it causal. So this is 0. We're going to shift the impulse response. So this is the ideal, this is practical. Sounds good? Okay, so let's see what the impact of this windowing is going to be on the frequency response. So this is our h of n that is going to equal to, let's keep it as h of n. So let's start. Let's look at the impact of windowing on the frequency response. What happens when we window the impulse response? So let's take an impulse response that is infinite and see what's going to happen to it. So starting with h of n. This h of n is ideal, and therefore the frequency response looks like a rect, and this is omega. How do I know what happens to this frequency response when I window the impulse response? Any ideas?
It's not going to be as steep.
Okay. How do I know exactly what's going to happen to it? What does the windowing look like in the time domain? looks like multiplying the signal with the rect, isn't it? If I multiply this signal with a signal that looks like this, so this is a window. If I multiply these two signals, what's going to be remaining of this signal? Only when this signal is 1. It is 1 and 0 otherwise. Does that make sense? When we multiply them together, what's going to remain? Only the signal components that are within the window. So what's going to be remaining? It's going to look something like this. Something like this. Make sense? We're multiplying these together. 0 is going to cancel anything here. This is 1, so only these components are going to remain. How do I know what the impact of this on the frequency response? Yes, I can use the convolution. So I'm going to take this window. What is the frequency response of a window like this? A sink in the time domain, give me a rect. A rect in the time domain, what is it going to give me? A sink. So if I look in the frequency domain, this looks something like this. This is W e to j omega. Now if I multiply these together in the time domain, what is the frequency response going to look in the time domain? It's going to be the convolution of these together. Does that make sense?
Yeah.
This multiplied by this is going to have a spectrum that is this convolved with this. So this is a convolve and therefore I'm going to get a frequency response that looks something like this. Together? So the windowing here is going to give me the convolution of the sink with this. What happened to the rectangular pulse that was ideal, the rectangular shape? It became smeared. And you see it? Instead of this going like a sharp edge, now it's smeared. And we have also ripples in the response. And again, this is just a direct result of the convolution of these two signals. Okay, so therefore, the windowing that we've done to make this filter practical resulted in smearing of the frequency response, and it resulted in ripples in the frequency response. Okay. And of course you can, you know, when we make this window bigger, what's going to happen to this thing? It's going to get narrower, and therefore this transition is going to get sharper. Does that make sense? And vice versa. If I make it shorter, then this is going to get wider, and then this transition is going to get wider. So apparently the length of the window, the width of the window, is going to impact this transition that I have here. Okay. So therefore, this is one of the windows that we can use to take the ideal filter and get a practical filter. What do we call this window? A rectangular window. Make sense? Looks like a rectangular window. So therefore, we're going to be looking at different windows that we can use to take this ideal filter and get a practical filter with. So the first window is a rectangular window. And the rectangular window, W of n, is going to equal to 1 when n is greater than or equal to negative n minus 1 over 2, and is going to be 0 elsewhere. And for the rectangular window, W of e to j omega is going to equal the summation from n equal negative n minus 1 over 2 to n minus 1 over 2, 1 multiplied by e to negative j omega multiplied by n. And this is, we can show that this is going to equal to sine omega multiplied by n over 2 divided by sine omega over 2. And therefore, the rectangular pulse, or the rectangular window, from negative n minus 1 over 2 to n minus 1 over 2 is going to have a frequency response that looks something like this. Something like this. Now this is going to equal to 2 pi divided by n. This is going to equal to 4 pi divided by n. This is going to equal to negative 2 pi divided by n. Okay. The other thing we need to know that this, we're going to call it main lobe. And these, we're going to call it, or we're going to call them side lobes. Got that? So therefore, for this window, we have a main lobe, or the main lobe width is going to equal to 4 pi divided by n. The 2 pi and 2 pi. So this width is equal to 4 pi divided by n. Now, what is the impact of this main lobe width on the filter design? Yes, it's going to determine how the filter is going to transition from the pass band to the stop band. So this width here is determined by that main lobe width. Together? Okay. Go ahead. Okay. Now the second metric of the rectangular pulse is that the maximum side lobe amplitude is equal to negative 13 dB. So if I normalize this, and this is a 0 dB, this is going to equal to negative 13 dB. And finally, the maximum ripple in h of e to j omega that is due to rectangular pulse or rectangular window is equal to negative 21 dB. Does that make sense? What does that mean? The maximum ripple in h of e to j omega. If I looked at the frequency response of this filter, then the maximum in the stop band is going to equal, because of the rectangular pulse, is going to equal to negative 1 dB, negative 21 dB. Not clear, is it? Clear? Not clear? Okay, we'll see it. We're going to run some MATLAB and we'll highlight it. So just keep it in mind that there are these numbers that we are interested in, and these are going to determine the performance of the filter. So this is the case for a rectangular pulse, but nobody said we have to use a rectangular pulse. We can use other windows. And one of the other windows that we can use is the Hamming window. So these are the parameters for a rectangular pulse. We can use a Hamming window. And the Hamming window, instead of the case of a rectangular pulse just being a constant, the Hamming window, the window is given by 0.54 plus 0.46 multiplied by cosine 2 pi multiplied by n divided by n minus 1, and 0 elsewhere. And this is going to look something like this, the window itself. And again, we're going to run MATLAB and we'll show you how these windows would look like. But unlike the rectangular window where it's closed, where it is constant, this has this shape. Now, since the window has a different shape, it's going to have also different parameters when I convolve it with the ideal filter. So this filter is going to have a main width that is equal to 8 pi divided by n, and is going to have a maximum ripple in resulting h of e to j omega that is equal to negative 53 dB. Okay. Now there are other windows as well. So we have Hanning, we have Blackman, and we have Bartlett. So all these are different windows that we can use to design our filter.
I think you've got the range for the first one, WN.
And WN.
For the Hamming window.
0.45.
You just put the equation, not the range.
What does that mean?
Is the cosine the range?
The
Or
range?
the piecewise function?
I mean, all of these are from n minus 1 over 2 to n minus 1 over 2. We're not clear. W of n, 0.54 plus 0.46 cosine 2 pi multiplied by n over n minus 1.
So when n equals 1.
So n defines the window.
All of these are the same window, n minus 1 over 2 to n minus 1 over 2. N defines the width of the window. Okay. So let's look at some MATLAB and plot these windows and see how they look like. And then we're going to see how these windows will impact the design of the filter, and that is what we are interested in. Here is the FIR windows. Okay. So this is going to plot the rectangular window, the Hamming, and the Blackman window. And these are all MATLAB comments, like they are defined in MATLAB. So the length is 30, and I'm going to plot the filter or the window in the time domain and the frequency response of it. So this is the rectangular window. This is our Hamming window. And this is our Hamming window. And this is our Blackman window. What is the difference between, if you look at these windows? I mean, the time domain, these almost look the same, aren't they? I probably have to put them on top of each other to notice the difference. The difference is minute, but nevertheless, they're different. I mean, you can see these have a magnitude, this is 0 here. All of these are of length 30. Nevertheless, when you look at these windows, the difference between them is this width, the width of the side lobe, and how much attenuation I have here, how much the width of this, and how much attenuation I have here, the width and how much attenuation I have here. Make sense? And again, this is going to play an important role in the design of the filter, as we will see. Okay, so let's take these and paste them in a new page.
So there's a Hamming with an M and there's a Hamming with an N.
That
Yes.
won't be confusing, remember?
I don't have to remember them. You can use a formula sheet.
What about Bartlett?
I don't have it, but you could add it if you like.
Okay.
I mean, these enough to highlight the differences between them. And I don't want this to paste like this, so therefore I'm not going to paste it. Instead, I'm going to paste this table here. That highlights the differences between these different windows. So how much is the peak side lobe amplitude? A rectangular is negative 13, Hamming negative 31, 41, negative 57. And how much is the width of the main lobe? And how much is the peak approximation error, dB, in the resulting filter? Negative 21, negative 25, negative 52, negative 74. And we'll see what this means in a minute. Does that make sense, what these numbers are? So what these numbers, so this negative 13 is this number here. Negative, what is this, a Hamming? This, for a Hamming, is this, and so on. And the width, similarly, this is the width, the width of these filters. Okay, so let's look at the filter design. And hopefully, when we look at the filter design and do an example, it will help us understand how these different windows impact the design of the filter. So how do we design FIR filter? So the first thing, we're going to convert the continuous frequencies or the continuous filter specs to discrete time frequency or discrete time specs. Omega equal W multiplied by T. We're going to have a passband frequency, omega passband. We're going to have a stop band frequency, omega stop. And we're going to have a maximum stop band ripple. And we're going to have a center frequency W center. And the center frequency is going to equal to WP plus W stop divided by 2. Okay. The second step, we're going to obtain the ideal response. So therefore, we're going to have a filter HD of N using W center. The third step, we're going to select a window from repo specifications. Then we're going to select the filter length. From delta omega. And then we're going to apply the window to the ideal HD of N. And we're going to shift by N minus 1 to make it causal. N minus 1 over 2 to make it causal. Okay.
So there's no pole zero, there's no manual method here, it's all.
Yes, there is no, well, there's no poles and zeros. You know, the FIR is always stable. And the only thing we worry about is the transition and the ripples in the stop band. We'll see. We'll see it in a second. Okay. So as an example, we're going to do two examples. We're going to do a low pass filter and then going to go a band pass filter. We're going to design a causal low pass filter that is FIR to meet the following specifications. The sampling frequency is equal to 10 kilohertz, and we have attenuation in stop band. We want it to be greater than or equal to 30 dB. And the filter looks something that we want, looks something like this. This frequency is 2 pi multiplied by 1,000. The stop frequency is 2 pi multiplied by 2,000. And we want the attenuation here to be at 30 dB. Okay. So what is it we're going to do, or the way we design this filter? The first thing, we're going to take all the frequencies and we're going to convert them to discrete frequency, W multiplied by T, which is W multiplied by 1 over 10,000. And therefore, we're going to have omega pass that is going to equal to 2 pi multiplied by 1,000 divided by 10,000, which is going to equal 2 pi over 10. This is this frequency here. Then we're going to have omega stop, which is going to be 2 pi multiplied by 2,000 over 10,000, which is going to be 4 pi over 10. And then from these two frequencies, we're going to calculate omega center, which is going to equal to 2 pi over 10 plus 4 pi over 10 divided by 2, which is going to equal to 3 pi over 10. Okay. So therefore, my ideal filter is going to look something like this. Ideal filter, and that line was crooked. Okay, my ideal filter is going to look like this. What is this frequency? 3 pi over 10. So these frequencies, when we map them, this is 2 pi over 10. This is 4 pi over 10. We took the center of them, and we said, okay, that is going to be our filter. Our ideal filter is going to look something like this. Together? Where this is coming from? Okay, so our ideal filter, HD of n, is going to equal to sine 3 pi multiplied by n over 10 divided by pi multiplied by n. Okay. Again, this filter is infinite in length, and therefore we have to window it. Which window we have to use? We're going to look at the stop band gain, and the requirement, we want the attenuation in the stop band to be greater than 30 dB. Together? So therefore, we're going to go to the filter design table that we had here and see which filter is going to give us, we're going to look at the delta and see which filter is going to give us in the stop band more than 30 dB. So apparently we can use a Hanning, we can use a Hanning, you can use a Blackman. Together? So this is, we're going to use a Hanning, which gives us negative 53 dB. So the third step, we want the stop band gain, which is the 20 log delta, to be less than negative 30 dB. And therefore, we're going to select the Hamming window, which give us a ripple magnitude that is negative 53. So we are erring on a safe side. We want less than 30 dB. The Hamming will give us negative 53. Does that make sense? Okay. Again, when we do the MATLAB, we'll highlight these points where these coming in. Okay, so finally, we need to know how wide the window is, and therefore we need to find n. And to find n, we're going to calculate delta omega, which is equal to omega stop minus omega pass, which is going to equal to 2 pi over 5 minus pi over 5. And we want this to be greater than or equal to 8 pi divided by n, which is the width of the main lobe in the Hamming window, 8 pi divided by n. So this is the width of Hamming main lobe. Okay, so therefore from this equation we have to have n that is greater than 40, and therefore we're gonna choose n to equal to 41. Anytime we get an n that is even, we'll choose the odd number that is above it. Okay. Okay, so finally, from W of n and HD of n, or we can H of n, and then we have to shift it by 20 to make it causal. So therefore, h of n is going to equal to sine 3 pi over 10 multiplied by n minus 20 divided by pi multiplied by n minus 20 multiplied by the window, which is the 0.54 plus 0.46 multiplied by cosine 2 pi over 40 multiplied by n minus 20. And this is when n is between 0 and 40. And when n is equal to a 20, this is going to equal 3 over 10. Any questions? Again, this is the ideal filter. This is the window, the Hamming window. We shifted everything by 20. The total length was 41. So there's a 20, a 0, and 20. We shifted everything by a 20.
What's the range on that n again?
N is 41. N is 41. So the filter is going to have 41 elements. 20 at the center and 20.
So what did it?
So there is at 0 there is element, and there is 20 elements here, 20 elements here. This is not causal. So we're going to shift everything by a 20. So it starts at 0. Make it causal.
So that's 0 to 40?
It's going to be coming out from 0 to 40. Therefore, it's 41 because the 0. Okay. So let's run this. Go ahead.
Finish writing.
Okay, let's run this MATLAB. Now our MATLAB, what MATLAB is going to do, so I'm going to, I have the filter, and I'm going to give the MATLAB the center frequency and the length of the filter. So it is 41, and omega center was 0.3 multiplied by pi. Together? Why did I not specify that I wanted to be Hamming? Because the default is Hamming. So if you design with MATLAB, the default is Hamming. Unless you tell MATLAB use another window, it will use the Hamming. Okay. That's not what we want. Okay. So here is our filter. Both in dB and in without a dB. So if you look here, this is determined, this one is determined by the window that we choose. Make sense? So negative 53, this is the Hamming window, is going to give me at least a negative 53. Have I chosen a rectangular window, this would have been high enough that I would not be able to meet the 20 dB requirement. Does that make sense, everybody? Okay. So two things. This is determined by the Hamming window, and this transition from the pass band to the stop band is determined by the main low width. Remember, this used to be an ideal filter. I convolved it with the sink. It gave me this transition. This width is determined by the sink. That is coming from the window that I choose. Make sense?
Yeah.
Okay. Okay, let's do another example. And in this example, we're going to design a causal band pass filter according to the following specs. We have a 2 pi multiplied by 3000 here. This frequency is 2 pi multiplied by 4000. This frequency is 2 pi multiplied by 8000. And this top frequency is 2 pi. 2 pi multiplied by 9000. This is W. And we want the stop band attenuation to be less than negative 40 dB. And our sampling frequency, if sampling is equal to 24 kilohertz. Okay. So the solution, we're going to convert all the frequency to discrete frequency. So we're going to have omega 1, 2 pi multiplied by 3000 divided by 24,000, which is the sampling frequency. This is going to give me pi over 4. I have omega 2, that is 2 pi multiplied by 4,000 divided by 24,000, which is going to be pi over 3. I have omega 3, which is 2 pi multiplied by 8,000 divided by 24,000, which is 2 pi over 3. Omega 4, which is 2 pi 9,000 over 24,000, which is 3 pi over 4. So therefore, my frequencies look something like this. I have pi over 4, pi over 3, 2 over 3 pi, and 3 over 4 pi. Okay, so we're going to calculate two frequencies. Since there's two transitions, I'm going to calculate omega center 1 and omega center 2. And omega center 1 is going to equal omega 1 plus the average of omega 1 and omega 2, which is going to equal to 7 pi over 24. And I'm going to calculate omega center 2, which is going to be omega 3 plus omega 4 over 2, which is going to equal to 17 pi over 24. So this is going to give me the ideal filter that we can start with. So from here, my ideal filter is going to be HD of n equal to sine 17 pi multiplied by n over 24 divided by pi multiplied by n minus sine 7 pi multiplied by n over 24 divided by pi multiplied by n. Our ideal filter. Okay. So next, we want the stop band attenuation or the stop band gain to be less than 40 dB. Stop band attenuation to be 40 dB, or the stop band gain to be less than negative 40 dB. So we're going to choose again Hamming. Which is going to give us a negative 53 dB. Bless you. Again, we have the stop band attenuation that is specified to be 40 dB. So from that attenuation, we go to our table and see which one is going to be able to give us 40 dB. And since the Hamming can give us negative 53, we can choose the Hamming. The next step is to find the value of n, how much the window size has to be. And to do that, I'm going to go to the graph that we have here, and I'm going to calculate delta W here, and delta omega here, and delta omega here. And in both cases, I'm going to have delta omega that is equal to pi over 12. This is equal to pi over 12. Again, this is the width of the transition. This width is pi over 12. This width is pi over 12. And since we chose our Hamming window to be Hamming, then we want delta omega, which is equal to pi over 12, to be greater than or equal to 8 pi over n. Again, this is from tables, from the Hamming table. Hamming 8 pi over n. Together? So therefore, this is going to give me the value of n. And we want n to equal to 97. Since it's odd, we keep it odd. And finally, we can write h of n. And our h of n is going to equal to
96. And then we go to 97.
I'm going to squeeze everything so we finish all this in one page. Okay, so h of n is going to equal to 1 over pi multiplied by n minus 48 multiplied by sine 17 multiplied by pi over 24 multiplied by n minus 48 minus sine 7 pi over 24 multiplied by n minus 48 multiplied by 0.54 plus 0.46 cosine of pi of n minus 48 divided by 48. And this is when n is between 0 and 96 and not equal to 48. When it is equal to 48, it's going to be 5 over 12.
Quick question.
Mm-hmm.
Is it 0.54 plus that quantity times just the second sign or both signs?
Yeah, so is there, you have an opening square bracket on the left side, is there a closing square bracket to match that?
Yes, I mean this sign, there's a square one here. This sign, the sign, the ideal filter multiplies the window. And this 5 over 12 is the 17 pi over 24 minus 7 pi over 24. over pi, which is this over pi. Okay.
So is the n equals 48, is that like
The center.
the center?
The center before we shift it. Does that make sense? But it's going to be the center of the shape. We will plot it now. Bandpass filter. Maybe I should not plot. Where is plot? Okay, I don't want this one. I want these two. Okay, so this is my filter at 48. It's equal to this value. It's of length that is 97. And if I look at the attenuation in the stop band, it is a negative, it's greater than negative 53, which we want it to be less than 40, and therefore we meet that.
So why isn't there any ripple in the passband?
In the passband, why will there be a ripple?
Well, it's a bunch of signs, right? So you'd think there'd be some.
In here, there is ripples, there is a sink. In here, this is an ideal rect. Good. Convolved with a sink. Now this whole area is going to be just a constant. The ripples are going to start at the ends. Does that make sense? And this is much wider than the width of the sink. Actually, there is, stay with me. Let's do one more example, which I probably should have done at the very, very beginning. Let's do this one. So there is another code that we wanted to do. Oh. Okay. So this shows what we've been doing using a rectangular window. So we have our, this is the filter, the ideal low pass filter. This is the window that we're going to choose. And be careful. This is what happens when we convolve a sink with a rectangular window. So even though this is in the time domain, we really want to see this as if it was in the frequency domain. Does that make sense? So what happens when we convolve them? We're going to have these ripples, but this is going to be just at the very end, which we can see if you. I don't know if you can see them here, but this is not a straight line. See, there is a ripple that looks like something like this. And of course, it's in dB, so it's slightly different. See this rippling here?
That's what I expect from the other one.
Yeah. Yeah, I mean, they all will have it, but it's so small compared to
Okay.
how big the scale that we have. I mean, here we had it, I mean, apparently like more than 50 dB, so this is very minor, very small compared to it. Does that make sense, everybody?
Yeah, it was confusing to me that it was perfect. It looked ideal, but. in
Yeah,
the
it should-
it's a
it should-
Small bit of ripple.
Yeah, there is a ripple. I mean, just like there is a ripple in here, a tiny ripple, there is, all of them will have a tiny ripple at the transitioning from the stop band to the pass band. And again, this is what we see in here. Because that's in dB, so it gets it smaller. Any questions? Thank you, everybody.